Hi students. So today we're going to discuss about a topic from aldehyde and ketone, that is nothing but nucleophilic addition reactions of aldehyde and ketones. There are plenty of reactions from aldehyde and ketones. Among those reactions, this nucleophilic addition reaction is something important reaction, because we know that every year there is a question from this side of this topic of the aldehyde and ketone. So now let's start with the mechanism of the reaction. So before we starting with the mechanism, we have to know why actually aldehydes and ketones are undergoing nucleophilic addition reaction, right? So for that, we have to know the structure of aldehyde and ketone. So this is the structure of aldehydes and ketone, general structure. There will be this carbonyl group, and there will be any R group. R group could be alkyl, aryl, or hydrogen atom. Okay. So from this structure, we can see that how a carbon-oxygen bond, like a CO bond, will be polar. And why is that? We know that oxygen is more electronegative, and thereby it is more electron withdrawing. That makes the CO bond more electronegative. So as CO bond is more electronegative, the bond will shift in this way, and the resultant structure will be like this. Okay. So now from this structure, it is very clearly visible that a carbonyl carbon has positive charge. A positive charged carbon, we know that is an electron deficient center, and an electron deficient center means it's an electrophilic center. And due to the presence of this electrophilic center, nucleophile can easily attack to the carbonyl carbon, right? So this electron deficiency of the carbonyl carbon make aldehydes and ketones undergo nucleophilic addition reaction. So now we know why they are undergoing nucleophilic addition reaction. Okay, so that's clear. So next we can have a look at the mechanism of the reaction. So the mechanism. See, for the mechanism, I'm drawing the structure of the carbonyl compound this way. So we can see that this carbon has the hybridization of sp2 hybridization. Since it has a sp2 hybridization structure, it will have a trigonal planar geometry. So this whole molecule lie in a plane, okay, in the same plane. Okay, so the carbonyl group is lying in a plane. So just think about it. When a nucleophile is attacking the carbonyl carbon, from which side it can easily attack to the carbonyl carbon? See, this is carbonyl carbon. Carbonyl carbon is here, right? So the nucleophile can either attack from the top in this manner or from the bottom side. So the easiest attack would be in a way perpendicular to the carbonyl carbon. Ready? And there is two ways of attack, either from the bottom side or from the top side. So either it could be this way, nucleophile attack, or it could be this way, nucleophile attack. Okay, so that is the nucleophilic attack possibilities, and that attack will be the slowest step. Since the step is lowest step, we know that that is the rate determining step. Rate determining step. What is the speciality of the rate determining step? It will decide whether the reaction will take place at the fastest rate or at the slowest rate. We already know that part from the reaction mechanism, also from the chemical kinetics. Okay, so let's say the nucleophile is attacking from the top side, so that may lead to the formation of an intermediate like this. When the nucleophile attack to the carbonyl carbon, the bond shift in this direction, and thereby it results structure like this, R. Okay, one is R dash and the other one is R. Okay, So just after the attack of the nucleophile, there will be the attack of electrophile. Okay. So the structure formed right now is called a tetrahedral intermediate. Tetrahedral intermediate. See, this tetrahedral intermediate is undergo attack of electrophile next. Okay. So the attack of electrophile may result in the formation of this final product as this OA. And generally this electrophile could be H plus. In general cases, most of the cases electrophile will be H plus, like proton will be the electrophile. So now this is the product. So just to have a look at the final product, how final product is chiral. And why this product is chiral? Because we are having all different valencies on the tetrahedral carbon. So we can now understand one point here. When we are starting with a compound like this one, like when we are having two different groups on the carbon attached, that may result in the formation of chiral molecule, the chiral compound. Okay, actually such compounds which may turn into a chiral compound is called a prochiral compound. So maybe we can say here we have started with a prochiral compound, and that is where we are getting a chiral compound. Okay. Again, what is prochiral compound? A compound that may change into a chiral compound just by changing one of the valencies. See, we had two valencies satisfied by oxygen, but now here once we change one of the valency, we are having four different valencies on the tetrahedral carbon, and that is why the compound is chiral. The product compound is chiral. So what is the speciality of the chiral compound? See, if we are having a chiral molecule as a product, we know that the chiral molecule will have its enantiomer. So which means there is possibility of formation of two types of product, like two stereoisomers will be there. Okay, that may be called as enantiomers. So we can say there will be formation of enantiomers. Enantiomers are the stereoisomers which are actually that can be defined as non-superimposable mirror images. Like if you are having a product like this one, there will be exact mirror image of this one. See, you will have the exact mirror image here. This time OE will be here and the others will be in this manner. So that is it. So the products will be enantiomers. And we know the formation of these two enantiomers are 50-50 chance. Like if the nucleophile is attacking from the top, it may result in one enantiomer, and if the nucleophile is attacking from the below side, bottom side, it will result in the another enantiomers. So that's why that is why enantiomers are formed, right? So the possibility of attack from the both side is 50-50, and thereby the formation of enantiomers are 50-50, right? So, and also we know that if there is 50-50 formation of enantiomers, that mixture of product is called racemic mixture. So we can say racemic mixture. We can say there are formation of enantiomers, or simply we can say enantiomers are formed. So racemic mixture is formed. So that is it. So that is a stereochemistry part of this reaction. That is very important for the JEE examinations. Okay. Now, prochiral, chiral, enantiomers, racemic mixture. So you don't have to think much what is prochiral compound. In this case, you just have to look at the structure of the aldehyde or ketone that you are starting with. If you are having two different groups attached here, that definitely will result in the formation of enantiomers. That is racemic mixtures. So you don't have to worry much. Okay. So this is the mechanism of the nucleophilic addition reaction. So simple mechanism, that is it. Okay. Now we understood how the reaction is taking place. Now we can look at reactivity, like which one will react at fast rate or which one will react at slowest rate. So for that we have that slower step or nucleophilic rate determining step, right? So listen, we all can see that attack of nucleophile is the slowest step, and that is the rate determining step. So if you are starting with, if you are comparing between two aldehyde and ketone, aldehyde and ketone. See, the reaction is slowest step is attack of nucleophile to the carbonyl carbon, to the carbonyl carbon. See, to the carbonyl carbon. And if the attack is taking place at easiest rate, then the reaction will proceed at a fast rate. That is it. That's a simple logic. So if my nucleophile can attack to the carbonyl carbon so easily, then the reaction will be at fast rate. Okay. So look, when we look at the aldehyde, there is only one R group and the other one will be always hydrogen atom. In the case of ketones, there is one R group, also one more R group. Ready? One more R group. So this additional R group make my nucleophile, make my aldehyde, so ketone, more bulkier, and thereby thereby the attack of nucleophile will be less effective, or maybe we can say the attack of nucleophile will be more difficult, right? Because since there is steric hindrance, the attack of nucleophile won't be that easier as there in the aldehyde. Okay, so we can say the additional R group present, the additional R group, alkyl group, or R group, simply R group, make the attack of nucleophile difficult due to steric hindrance. Okay, so from that point we can easily say ketones undergo the reaction at a fast rate. Sorry, ketones will undergo the reaction at the slowest rate. There is one more reason for that. Okay, we all know nucleophile is interested on the carbonyl carbons, electrophilicity of the carbonyl carbon. If the carbonyl carbon is more electrophilic, then the attack is so easy to take place. So again, look at the structure. We are having one R group only here, and that R group we know they are electron releasing groups due to their plus I effect. When we check on the ketones, there are two R groups and they are plus I group. Okay, plus I groups. Since they are plus I groups, they are releasing more and more electron density to the carbonyl carbon. So in the case of aldehyde, there is only one maximum possibility of one R group, but in the case of ketone, we can clearly see there are two R group. So one additional R group making the carbonyl carbon more less electron deficient. Means it is no more that electron deficient as in the case of aldehyde, right? Or we can say less electrophilic. So in the case of ketone, our carbonyl carbon is less electrophilic. If the carbonyl carbon is less electrophilic, then the attack of nucleophile won't take place at that fast rate. And if the attack is not taking place at fast rate, it means the overall reaction is taking place at the slowest rate. So we can clearly say now ketones undergo the reaction at the slowest rate. So the second reason was additional R group. Again the additional R group. Okay, make the carbonyl carbon less electrophilic. Okay, and that's why we can simply say ketones are less reactive towards nucleophilic addition reaction. nucleophilic addition reaction. Okay, simply NAR, nucleophilic addition reaction. So now it is clear. Now let's just combine few aldehydes and ketones here. We are having three different. One is this aldehyde, the other is ketone. See, in the first case, there is only hydrogen atom, which won't make the molecule bulkier, or it is not an electron releasing group as well. But again, the case of second aldehyde, there is one R group which is electron releasing, and in the case of ketone, there are two different alkyl groups. So it is clearly visible from this structure as well, which one is more reactive. First aldehyde is more reactive than second aldehyde, and it is more reactive than ketone. Okay, that is it. And in the case of aldehydes, among aliphatic aldehyde and aromatic aldehyde, okay, aromatic aldehyde. See, here there is R group, and the electron releasing effect is due to inductive effect. But in the case of aryl group, this benzene will be releasing the electron through resonance effect. So one is releasing the electron density to the carbonyl-carbon through inductive effect, and the other one is releasing the electron density to the carbonyl group through resonance effect. Which one is stronger effect? We all know that resonance effect is a stronger effect. And thereby, in the case of aromatic aldehydes, aryl aldehydes, there will be more electron released to the carbonyl-carbon, and thereby the carbonyl-carbon will be less electrophilic. So if the carbonyl-carbon is less electrophilic, reaction takes place at a slowest rate. So in the case, aliphatic aldehydes are more reactive towards nucleophilic addition than aromatic aldehyde. Clear? Now let's have another question. Which of the following will give enantiomers as the product of nucleophilic addition? Okay, nucleophilic addition. So we are having three different aldehydes and ketones here. In the first case, just imagine what will be the product in the case of nucleophilic addition. Okay, so here there will be OH, and the nucleophile will be attached to the carbon and the hydrogen hydrogen. So just look at it. This compound is not at all chiral. So if you are starting with a compound having same groups attached to the carbon, they won't result the formation of chiral compound, and thereby there won't any enantiomers production. Ready? So in this case there is none. So same is applicable in the case of third one. Right? We are starting with a compound having two same groups on the carbon, so it won't result in enantiomers. But in the case of second one, there are different groups attached to the different groups attached to the carbon. So these compound can be called as a prochiral compound. So this will result in the formation of chiral product, and thereby enantiomers will be the product. Right? So that is it. That's it for today. Thank you.